Welcome. It's great to have you all here with us. One of the great fields in science is electronics, and a lot of you have probably learned a lot about that with Dr. John's STEM 3 electronics class. That's a great place to learn things. But I want to tell you a couple of things that he probably didn't tell you. For example, if an electrician tells you the problem is a high impedance air gap, what he means is you didn't plug it in. And when I tell you that I used organic grounding, I got shocked. That's what I'm telling you. Okay, a couple of little terms that'll help you out. Well, a little bit of science news. The James Webb Space Telescope has been hard at work, and an international group of researchers were recently able to detect enormous clouds of helium that are drifting away from a planet. It's an exoplanet called WASP 107b. And this is really interesting because, normally with an atmosphere, it kind of holds in, and thank goodness the Earth mostly holds in our atmosphere. But this particular atmosphere is just getting dissipated off this giant cloud, and they're theorizing it's a little too close to its sun. It's as close to its sun as Mercury is. So, and they're able to spot this. It's the first time they've been able to use the James Webb to be able to detect this particular type of gas. And they're learning a lot of interesting things about planets. This one is 210 light years away, but they're able to spot that from that distance, which is pretty exciting. We're learning more and more things about this huge, huge expanse that's out there. Well, it's time to get it over to Dr. Joshua for How to Study with Acellus Gold.
Well, I have some exciting things to talk about, but first I want to talk real quick about the Acellus app. Some students have written into us and said that they're using Acellus Gold and they're having some trouble with the Acellus app. And what a lot of people don't realize is that in Acellus Gold, we have all of this high definition video. You have the ability to watch these incredible videos of your teachers, and some of the older processors and older computers have a hard time processing that high resolution video. And so you might find that if you're using a computer that's a little bit dated or a little bit older, in addition to installing the app, you may want to look at using a computer that's a little bit newer that has some of the features to take full advantage of the Acellus Gold learning experience. So something to keep in mind, if you do have trouble with using the app, be sure to give our support team a call. We have people that are available to assist and can help you figure out how to give your student the best learning experience. So now let's talk about some exciting things that are coming up. This time of year is really exciting because it's the college application season for students who are seniors. You're starting to take your big ideas and big dreams and bring them to life on paper. And so the class of 2026, it's such an exciting time of year to see what your plans are and what you're going to do. And last year, as you may have heard, our graduating class in Acellus Academy, the class of 25, was so big that we had to hold 11 different commencement ceremonies to accommodate everyone that wanted to come out to Kansas City and receive their diploma. It was so much fun to meet everyone, but we wish that we could have had our students come together and meet each other. And so this year, we're very excited because we have this brand new Acellus Conference Center. And this is going to allow us to hold a massive graduation celebration here in Kansas City, Missouri. So mark your calendars on Memorial Day weekend. On Saturday and Sunday, the 23rd and 24th, we'll be holding our graduation ceremonies for Acellus Academy in conjunction with Acellus World. This is a wonderful celebration for all Acellus students, but we'll also have our graduation ceremonies. And it's a great chance to come and meet your teachers. There's a lot of exciting things going on, but it's also a great opportunity to meet your peers in this wonderful class of 2026. So we'll have graduation activities going on, things like where you get to take your graduation memories book around and meet your different peers, and a lot of other exciting updates. And so if you want to stay tuned and see the latest information and the latest updates, go to acellus.com/world. You can see the information that's posted and book your tickets. And to give you a little flavor, here's just some of the highlights of Acellus World in 2025. Take a look. Well, we can't wait to meet you and celebrate your achievements. If you're not able to make it to Kansas City, we will be broadcasting live so you can tune in online as well. And keep studying hard. Thank you.
Well, it's time to get it over to Dr. John for the Technology Spotlight.
Have you ever had one of those moments where you're filming something really important and then you get that error out of disk space or out of storage, right? We are always running out of storage, and the problem's getting worse and worse because we have more and more data to save. And this is something that's been going on for a while, and researchers have been, trying to figure out different ways to store more data, more compact. Well, there's a really interesting idea that might solve this problem, and it's using DNA as the storage. Remember, DNA is the type of molecule that living organisms use to save information. So if they're doing it, couldn't we do it? I guess we already are, right? In fact, they estimate that in one living cell of a human, you have around 3.2 gigabytes of data in your DNA. That's a lot, and you have a lot of cells. So that's a lot of information, but why would DNA be a good way to store data? I want to take a look. Remember, DNA is shaped like a double helix, and there are actually 4 different molecules that they describe as letters, like the A, the T, the G, and the C. And one of those 4 letters fits in the pattern, and you can have any one of those and any pattern of those, but on the opposite side, it always has to match. And if you look at this, if there's an A, then you have to have a T on the other side. And if there's a T, you have to have an A on the other side. And the same thing with the G and the C. So if you have it set on one side, it always has to match on the other side. And that's a really important detail. You see how it kind of snips together or zips together, and it's a really sturdy shape? Well, the really neat thing about this double helix and this special configuration is how easy it is to duplicate. It's really hard sometimes to make a copy of data, especially when it's this small. But because of this special pattern where they have to match, it's actually surprisingly easy. First, you have to unzip the DNA so you have 2 pieces. And then if you put it in the right solution, only the right molecules will bond to fit with the A, T, C, or G. And so you can split it and then form 2 copies of it. And that's what our living cells do. They're always dividing and having the same DNA in both sides of the cells. And that's the way that it works. And this is a really neat property. I was thinking that it would have been an awesome thing to invent, if you'd invented DNA. Sounds like something R51 would say, doesn't it? But some researchers have been working on this for quite a while, trying to figure out how to make it work. The problem is, you've got to somehow have the DNA hook up to a computer, right? Well, a startup actually has a product that you can buy that does this. They call it the Atlas Eon 100. And here's what it looks like. Looks like a little pill you could swallow, doesn't it? Not that kind of DNA, right? But really, they take some DNA, they dehydrate it, and then when it's a powder form, they put it in a little capsule. And this capsule will stay for a very long time. When we think about storage, if we're talking about flash drive, or like flash memory in your phone, or maybe a magnetic storage, they have magnetic tapes that'll store a lot of data, or magnetic hard drives. We're talking somewhere around 10 years of storage, and then you start losing data. Well, then you could do the optical discs, like CDs or DVD discs. And that's more like 25 years, but you have to make sure that it's in a good condition, because there are funguses that'll actually, or viruses that'll eat the data off. So you have to make sure that's all good. So we're talking about maybe 25 years. But with DNA, we're talking about thousands of years. So it's a completely different ballpark. And so that's a really, really long time. Here is the process that they're using to do this. First, you have to take the ones and zeros of your computer data and convert it to the DNA letters. You have to have some way to convert that data in. And that's the easy part. And then you have to synthesize the DNA, the synthetic DNA, with your data. And then you dehydrate it, and you can make lots and lots of copies of it, of course, and save it as this powder. And then if you want to read it back, you have to take the powder, rehydrate it, and then sequence the DNA, and then you get your data back. So there's quite a bit to it to convert it to DNA and then to get it back. But you can store the data for thousands of years. And then the other interesting thing is really, really high density. If you wanted to save, let's say, 60 petabytes of data, that's a lot of data. We have to back up. So on your phone, you're talking about gigabytes. Maybe you have if it's a big one, it's 128, or I think maybe now they have 1,000 gigabytes, which is a terabyte. Well, a terabyte is 1,000 gigabytes, but a petabyte is 1,000 terabytes. So it's a lot of storage. Well, you can buy these huge racks that will save 60 petabytes of data in the rack. But they're doing the same thing, 60 petabytes of data, in a little box like this. They have these little racks of these little capsules. So we're talking about way more dense storage, and you don't have to keep recycling the storage media. Every once in a while, you might want to pull it out and make sure that it's good and everything and make more copies. But then you can save these little capsules in remote areas and have the data safe. And this might be really useful for anything that you really don't want to lose, like your family photos, right? Or maybe really, really good copies of our famous art and our music and anything like that we don't ever want to lose. Right now, if the magnetic copies that we have went bad and no one made another copy, then it would be lost. And so anything that's that important, it's a really big deal. Well, that's one form of doing the DNA. Another form of doing the DNA storage that they've been working on in China, some Chinese researchers, is to store the data on a cassette tape. And it looks like this. They actually have a strip that they store the little DNA molecules in, and they can store like 36 petabytes in one of these cassette tapes. And they're working on a more automated process to be able to write the data onto the cassette and read it off. So they're looking at making something that's more like a hot storage where you can use it more often. And again, the same idea, they can store much, much denser data, and they have a really long retention time. So this is moving from science fiction into reality. It's pretty amazing. And you're probably wondering, well, how long could you store data in DNA? They're advertising 1,000 years, but we've actually sequenced DNA from woolly mammoths that they estimate are over 1 million years ago. And so there's some really, really, really amazing possibilities here. That's a long time. Speaking of time, that's all the tech we have the time for. Thank you.
Now it's time for Breakthrough Moments in Science with Tobias.
So, how many times should you try something? Like if you're trying to invent something, how many times should you try before you decide to give up? You know, they say if you can laugh at, like, if you make a mistake or something goes wrong, do you press forward? And they say if you can laugh at your own mistakes, you can actually lengthen your life. Of course, if you laugh at your wife's mistakes, it actually shortens it. That's the way that works. But no, if you have an invention idea and it doesn't work, should you try again? Thomas Edison once said that the most certain way to succeed is to always try just one more time. And we're going to talk about an invention that would find its way around the world, but after a lot of tries. Now, we're going to jump back to the early 1950s when NASA was working on some new rockets and even missiles. And these are going to, shoot up, hopefully into space, and they needed a lot of fuel. And so they were going to make the shell of these rockets. This is during their Atlas mission. So this is before Apollo. And they needed a shell for the rocket. Now, they didn't have a ton of aluminum and titanium that they could use for this. So what they were going to make the exterior of the rocket made out of was a thin shell of steel. And so that was going to be the shell. The problem was what would happen to steel when it would sit outside. And of course, when you think about steel, now it turns out most metals, if they're in their pure state, they're actually what we would term as unstable. And they want to connect with something else to be happy. And except for gold. Gold's like, we're good. Gold is happy alone, but most metals, they want to get with something. And steel is kind of like that. And steel wants to connect with something else, something like oxygen, but it can't. It needs something to help the connection, It's like a French love story. But no. And it turns out water is one of the perfect things to help the steel connect with the oxygen. So that's why when you leave something metal outside that's iron or steel, it can start looking like this. And what happens is the outside layer of the metal gets moisture, like after a rainstorm or something, and that water helps it connect with the oxygen. And the oxygen, it makes it that ugly color, but more importantly to NASA was it actually weakened the metal. So they needed to have a solution that they could coat the entire rocket. Now you might think, well, just put some paint on it. Well, remember, every single amount of weight that you're adding to this rocket is going to require more fuel to lift. So they're really trying to be cautious of the weight. And these rockets are so huge. Can you imagine how many buckets of paint it would take to coat this thing? So they need a really thin layer of something, hopefully more thin than paint. So they reach out to this company, and it was this little company called Rocket Chemical Company. And it was 3 guys. And their one job was to come up with a solution, a formula of some kind of liquid that they could coat this rocket with, where no water, moisture, could get to the steel, so the steel couldn't connect with the oxygen. So it needed to keep the water off of the rocket. And so they started. Now, these were chemists. This was a chemistry job. They had to know their chemistry. And so they start working on this project. They've got to get a formula, the perfect mixture of different chemicals and different things to make water not get in contact with that still. Also has to be able to coat it very thinly. It's got to stay on the metal, and there are a lot of requirements. So they start working on it. They think they have it, and they make a formula, and then it's time to test it. So they go through the rigorous different tests they have to do, and it fails. So they try again, and they try again, and 10 tries later, 10 formula inventions. And it's not that when they finish it, they know right away. They have to go through a bunch of tests to see if it's going to work. And 10 tries, and they're all failures. So they try more. Eventually, they get to 20 different failed formulas. And it was different things. It evaporated too fast. So they put it on and it evaporated. Or it left a weird residue. Or it didn't keep the water off and there was still rust. So they try some more. Well, they get 30 formulas that all failed. They get to 35, 39 failed formulas. Maybe it's time to call NASA and say, so maybe we should just paint it. They try it one more time, some little changes, and the 40th try, it works. And they are able to make this special formula that will actually keep the water off the rocket. And they're so excited. They go to NASA, and it actually succeeds, and they're able to keep the water off. And it not only keeps it off, if there is moisture, it kind of pushes it away, and then it protects the steel. So they start to use this formula on the rockets. These 3 guys start noticing something, that some of the workers are taking some of the formula. What are you doing with that formula? Oh, it's really nice on bolts. It's nice on bolts? Yeah, it like loosens them up. Oh yeah, I love it on these because then they don't rust. And so the 3 guys started talking, man, we should make a product of this for the consumer. And one of them said, yeah, I've actually been taking it home for a while, and it's really nice. So they make a bottle, and they're going to call it Water Displacement 40th Formula. And then they shortened it to WD-40. And I love that on the bottom it says, another fine product of the Rocket Chemical Company. It was the only product at the time. But they got this out, and so in 1953 was when they started on this project with NASA. In 1958 was when they first got it on the shelves for consumers, so you could get this. And by 1960, so this is 2 years after they put it on the shelves, an average of 45 cases were sold per day. And it spread by word of mouth. They started giving it to people, like, here's a free sample, go try it. And people tried it, and they loved it. And they would come back and get more. And they started talking to people, so what do you use it for? And there were so many weird uses people were using it for. By 1993, in 1 week, each week, they were selling 1 million cans of WD-40. And with the formula, remember, they went through 40 different formulas for this WD-40. Guess what's in the formula? We don't know. Because they purposely never patented it, so they never had to tell what the formula was. They were probably like, man, if somebody wants to copy this, they're going to have to do 40 different tries to find it out. And then they took the list, because there is a list of what the formula is. I mean, they're still making it, right? They took the list and they locked it in a vault. And there is one human, this is the legend anyway, there's one human who knows that full list. Only one. Can you imagine that? You'd have stories to tell if that was your job. So what do you do, Eric? Oh, let me tell you. One person. But this formula, to this day, is the exact unchanged formula that they made for NASA originally, and it hasn't changed. And now, if you go to their website, they've kind of entrepreneured this into something that was one use, and it grew and grew and grew into all these different uses. And so they actually have 2,000 certified uses for WD-40 that you can go look up. Like, if you don't know why WD-40 is important, you can go look it up. You know, you can get gum off a shoe. You can, if your snow shovel sticks to the snow, put it on your snow shovel. Snow won't stick. Whoa, some of you are going to try that, I know. Your zipper gets stuck, you can unstuck it. Clean off dead bugs from your windshield. Who would have thought? Remove gunk from a peeled sticker. Wasp deterrent. Remove coffee stains. Cleaning permanent marker off dry erase boards, because none of us have done that. Loosening stuck Legos. If you're buying WD-40 for loosening stuck Legos, you have some life questions you might want to ask. No. But it grows, and it's turned into this worldwide phenomena from this little company that failed and failed and failed until they finally got something. But then they took that and they figured out a way to make it a product that could be used worldwide once they saw how good it was. So if you have a good idea for an invention or a breakthrough, don't give up. You might need to try 39 times or 40 or 41. Just never give up. Thank you.
All right. Well, it's time for me to introduce the father of hydrogen technology, Dr. Roger Billings. You know, as you may know, Dr. Billings was mentored by none other than Bill Lear, the inventor of the Learjet and so many other inventions. And Bill Lear was mentored by Thomas Edison. And just like Tobias was talking about, inventors run into challenges, and Dr. Billings has taught us a lot here about the optimism curve, you know, where you start out and things are really great, and then you run into the challenges. And there's a great quote from Thomas Edison. He says, "Nearly every man who develops an idea works it up to the point where it looks impossible, and then he gets discouraged. That's not the place to become discouraged." And of course, we learn with the optimism curve is that you slowly come back up as you start to eliminate those challenges one by one. And so that's one of the things that great innovators have in common. Thomas Edison, Bill Lear, and Dr. Billings. And it reminds me of another famous Thomas Edison quote that I think describes all of them. Thomas Edison said, "I never did a day's work in my life. It was all fun." Well, please welcome Dr. Roger Billings.
Have you ever wondered what Science Live would be like without Paget?
Oh, come on.
It'd be just like this, wouldn't it? Yeah. Maybe the clap should come out. Okay.
Hello.
Oh, this feels better, doesn't it?
Yeah.
This wouldn't be the same, would it?
Not for me.
Okay, well, it's an exciting week, an exciting thing to talk about, and I like WD-40.
It's an amazing product.
I
isn't
know
it?
3,000 uses.
Keep finding them, don't
It
we?
is really fun, isn't it?
It is.
Well, we are talking about inventioneering, and we're learning how to invent by going through the process of inventing radio.
Okay.
Remember that?
Yes, I do.
And last time, we talked about this thing called a coherer. And these little round balls made out of tinfoil cohere together when they're in the presence of a radio wave caused by a spark. And when they cohere together, they conduct electricity. And then if you disrupt them by tapping the container, they uncohere and they don't conduct. Mm-hmm. This is the early way that scientists figured out how to detect when there was a radio signal. And of course, the goal was to be able to transmit Morse code over a long distance without wires. And if you could detect when the transmitter was transmitting, you could tell if it was a short blast like a dit or a long blast like a da, and you could send Morse code, dit, 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 da, da, da. So, but to be able to do it, took a whole series, a whole string of inventions. And so now we're going to kind of go through some of those inventions. I want to see if I can lay the groundwork for the problem that we're up against. And I want you to keep in mind this end goal, and it's a goal that we won't achieve tonight, but we will achieve it eventually, so stay tuned. So here's the goal. How many of you understand how a vacuum tube works and how a transistor works? You've heard of them, but how many of you really understand what they do and why they're so important? I think that with transistors now being the secret that makes our computers work, our iPhones, our desktop computers, it's transistors. And now in a modern computer, we have billions of transistors. But who understands really how they work? And so my idea in going through this series of how we came to understand radio, how radio came about on this planet, we can eventually really understand transistors, how they work, how to use them. And boy, whenever you understand a concept like that, it puts a new tool in your toolbox of invention because you can use that idea. Now remember, it's almost spooky science that these little balls made out of tinfoil in here will conduct electricity from one side of this glass to the other when there is a radio wave. And it's interesting, I create the radio wave by making this spark. The spark causes them to cohere, and so electricity flows, but then if you disrupt it, it shuts it off. But if you don't disrupt it, you can turn off the radio wave and the current still flows. So once they cohere together, they stay cohered until something jiggles them loose. So it's a fascinating magical phenomena. And you may remember that I have this hooked up so I can spark and I turn on my little LED light. But now they didn't have LEDs, so they couldn't turn on a little light, but they could tell that the current was flowing through this coherer. But now how can we send Morse code? And Morse code in those days was being sent over wires a long distance. And as the electricity was turned on the wire, on the other side, they had a little bell or a buzzer that would sit and buzz or would ring. And the guy that invented the bell is kind of an interesting fellow. I want to tell you a little bit about him. His name was Joseph Henry, and he invented the first bell back in 1831. I was in elementary school back then.
Were you really?
Well, maybe even before.
Or is that a long tail?
Yeah, maybe that was an exaggeration. But at any rate, he invented the first electric bell. And I want you to understand how these work because we're going to get into a discussion today, and it'll be very helpful if you understand these.
Okay.
So if you have a little round bell and you hit it with a spoon, ping, ping, it dings. But that's not electric. That's organic. Ding, ding, ding. What he wanted to do was make it ding when you hooked it up to electricity. Now, he was an expert on electromagnetism. Wrap a wire around a piece of metal, run electricity through it, it turns into a magnet. And so he came up with this idea, I'll have an electromagnet, and when I turn on the power, this hammer will swing and hit the bell, and I'll get a ding. And a lot of people had done that. That's pretty easy. But he said, now I want it to keep ringing. How do you keep it ringing? He needed an invention to be able to make it ring. I'm going to show you a picture here of an electric bell. In this bell, you can see there's the bell up on the top, and I hope you can see the little hammer there that's ready to strike the bell. And you can see the electric coil there. That's the magnet. And then there is the piece of metal over there that when the magnet turns on, it pulls the metal over and hits the bell. But something very, very magical happens there because on that bell, there's a little switch. Now let me show you another close-up shot of the same bell when it's turned on. Do you see how as the bell rings, it disconnects the switch. So think about that for a minute. You have this bell. When you turn on the power, it goes ding, but as it dings because the magnet gets charged up with electricity, pulls in the ringer, but when it pulls the ringer, it disconnects the power. So the electromagnet dies, so it flips back. When it flips back, it connects the switch again. So the magnet turns on, and so ding, 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 ding. So Mr. Joseph Henry came up with this wonderful invention, and he was so excited. This is a big deal back in 1831, and he wired it up, and the crazy thing started going ding, 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 ding. He was thrilled, and so he invited all of his friends to come and see it. And one of his friends, whose name we will leave out,
Why?
out of respect, one of his friends was a physics professor, and he leaned in way too close to examine the mechanism. And Joseph Henry said, hey, be careful. And this friend said, relax, relax. I've got a PhD in physics. I literally wrote the book on current flow. Electricity and I, we're on a first name basis. It calls me sir. I don't have to worry.
Okay.
But just then, he reached in a little too far and crack, pop, smoked the whole show. And he looked up kind of startled and he said, I stand corrected. It doesn't call me sir anymore. It calls me conductor.
Okay.
Get it? Electricity.
Yes.
Did you get
Yes,
that?
I got it.
I think that's kind of funny. Well, anyway, so that's how the bell came about. So with that little bell, and you can do the same thing with the buzzer. So it buzzes. Every time it buzzes, it disconnects the coil, so it flips back, and then it. So as long as the radio, as long as the key is pushed down, the buzzer will buzz. So you can hold it down short time, and on the far distant side, they can hear short buzzes. And you can hold down a long time, you can hear a long buzz, and that's how you can send dits and das, okay? Well, we've got to be able to do that over the radio. We've got to be able to send short and long things. This little spark transmitter just makes a pulse. It's just an instantaneous spark. But even when the spark's over, the coherer stays conducting. In their transmitters, they made spark generators that made big, long sparks that could last for a longer period of time. And so they could transmit things like DAWs, not just dits. They could do long pulses. But when the first detection was made by the coherer, it would lock up and it would just keep conducting. And so Marconi, according to the records I've read, was the one that came up with the idea of taking the little ringer on the bell and having it hit the coherer so that it would reset. So it would just go ding one time and it'd reset. And then as it would come back, if there was still a radio wave, if the spark was still transmitting, it would go again and again and again and again. And it'd keep going on, off, on, off, on, off. So that was clever to make that thing hit against the coherer and reset it. Does that make sense?
Yes.
Now, understanding that, I think we're ready to take a little detour over to Area 51, where I want to show you exactly what we had to do. Before we take off, though, I want to have one more piece with this. When we send electricity through the coherer, it's interesting that the signal that will go through these little balls, or in their case, they're using a little granular filings or powder, the amount of electricity, the current, even the voltage you can send through has to be very, very low, because if you have a high voltage, they always conduct. So to be able to turn it on and off with radio waves, it's got to be a very, very, very low current. That current wasn't enough to run a bell. A bell takes a lot of power to dang that ringer. And so if you hook a bell up to this, it's not strong enough to ring. And so let's go to the lab and see if we can figure out what the inventors came up with. Here we go. Hello, everyone, and welcome to Area 51. Can you remember from last time we were working with this coherer? These little balls of aluminum foil that we made are in this cup, has aluminum on the side, aluminum foil that doesn't touch. So the only way electricity can go through this cup is to go in this side, go through the balls, and come out the other side. And we found out that something almost seemingly magic happens when we put a spark on these. I've got this lighter, which had a little spark in here to ignite the flame. We took out the fuel. I called it propane last time, but it's actually butane. And then we go ahead and we spark it. And you can see it turns the light on. We tap it and the light goes off. Remember that? And remember what's actually happening is this spark is emitting radio waves. So the radio waves are going down, hitting the tinfoil, and when they do it, it makes them cohere together so they conduct electricity. That's why not the guy that invented it, but the guy that perfected it later called it a coherer, because it makes them cohere. But it's just a very light molecular thing. So when you cohere them with a radio wave, then you tap them, they uncohere. And that gives you a way of being able to detect whether or not there is a powerful radio wave. Is there a powerful radio wave in this room? Yeah. And we detected it because the light came on. Let's do it one more time, up a little bit closer. And there's the light. So that's pretty simple. But now the goal was to be able to send a radio wave over a long distance and be able to pick it up and tell what message someone is sending. The fact that the radio wave would turn the light on was not enough, because we needed the light to go on and off like Morse code. Dit, 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 da, da, long pulses, short pulses. And what happens when you turn it on, it stays on until you break the cohesion, then it goes off. So we needed a better invention to do that. It turns out that a very clever idea was thought up by a guy named Marconi. Marconi is famous for being the guy that really made radio practical. He took the idea of radio waves and he kept working on it and made it better and better. He would be what I would call the keystone inventor, because he's the one that took all these pieces that others had worked on and built it into something that people could use. He sold it. He made a lot of money from his radio patents and his radio projects. So here is an idea that Marconi had. He said, what if we hook this up to a bell? And if you look at this bell, it has a ringer, and when you put electricity through this coil, it pulls in on the coil, which pulls in on this thing and rings the bell. The problem is that once it goes in, it would stay in. And so they made the invention that right here is a little teeny switch. So as this goes in, it opens and closes the switch. So every time it goes in, the circuit is disconnected, which makes it spring back out, which connects the switch again and makes it spring back in. As a result, it sits and rings. And what Marconi did was quite ingenious. He came up with the idea, let's have this little ringer that's going back and forth, let's have it hit the coherer so that it will keep resetting it with every cycle. Pretty ingenious. And as long as it rings, there's a radio wave. If it's a long one, it's a dash. If it's a short one, it's a dot. So it was a great idea, but then he ran into a problem. This radio wave detector cannot detect a wave with enough power to be able to ring the bell. If I try to hook up a big battery so that this will turn on when there's a radio wave, this bell takes so much power to run this hitter, this electromagnet that makes the hammer hit the bell, that the coherer can't turn it on and off. And so he had a great idea, but he couldn't make it work. He needed to figure out a way to make this control a lot of power, not just a little bit of power. Now, in our example here, I'm turning it on with a radio wave, and we can see it turn on the light. But this light is very, very, very efficient. This is an LED, which they didn't even have then. The light bulbs they had wouldn't even come on with this kind of power. And so he had to find a way to make this device here work with a lot more power so it could turn it on when there's a radio wave and turn it off when there's not. Unfortunately, he was not able to do that. But he did come up with an alternative. You see, in this bell, there's a coil, and when you run electricity through a coil, it turns it into an electromagnet. That's what rings the bell. But you could also turn it on to just run a switch. And if you're trying to hit a bell, you've got to have a lot of power to hit it hard enough so you can hear it. But if you're just trying to turn electricity on and off, you could do it with a little teeny switch that wouldn't take much power. And we call the thing that does that a relay. And I want to remind you how a relay works, because it's a relay that's going to make this all happen for him. So here's what Marconi did. He took a couple of soup spoons. Actually, he didn't use spoons, but he made a relay. This is a relay. I've got 2 spoons. And as you can see, they want to touch here. And pulling them together is a coil of wire. This is a whole bunch of wires wrapped around a magnetic core so that when you run electricity from this battery through this coil, it pulls this spoon in. But you can see when I designed, and by the way, I have silicon in here to hold it, but you can see when I designed it, this is supposed to pop out when the electricity is turned off, and it doesn't. This is like so many inventions. It's a great idea. You want them to touch when there's electricity, and you want it to go off when there's no electricity. Well, it touches when there is, and it touches when there's not. But nobody needs that. So here is my invention. This is a piece of foam, little piece of foam ball, and I've cut it out so it'll stick in here. And guess what? I put it right inside this thing in just the right spot. And now look, can you see that the spoons aren't touching? But they will touch with just a little bit of force. So the sponge is kind of like a spring holding them apart. Now when I push on the button to hook up the electricity so this gets energized, watch what happens. Boom. I have made myself a spoon relay. You can run this while you're eating because it's a spoon. But can you see how clever that invention is? Now here's the big thing. When these spoons come together, it's like a switch. We can run a lot of power through them and they won't burn up because they're big, heavy pieces of metal. But this coil down here takes just a tiny bit of power, like you would be able to get from the coherer. And so by powering the coil, you can tell when there's a radio wave because it'll turn on, but it'll turn on something big. In this case, look at it. I have an actual extension cord here that I've run through these spoons. So I could plug this into the electric outlet. Now there's electricity. Be careful not to touch that because that's hot. And then I've got a little light here, which I'm going to go ahead and plug in. So you can see now, I'm set up to do something special here. If I push the button, the spoons will go together, and I should be able to turn on that light. And we're talking 110 volts. This is a lot of power. On 3, 1, 2, 4, I'm nervous, 5, 3, come on. But guess what? It takes that light a little while to warm up. What a stinker that is. It's on, and it's off. So I've created a relay. And this is one of the most important concepts you need to understand in electronics. As we go down into the future lectures, like next time and the time after, you need to remember and understand this concept because it's going to help you understand a lot of wonderful things like transistors, like vacuum tubes. So let's go through it again. There's a little coil here. This coil has a lot of windings of wire around a core. So when I connect this battery to it, it becomes an electromagnet. and it pulls the spoon into the other spoon, so the electricity going through the spoons connect, and it turns the light on. Bam, the light's on. On the other hand, when I let go of the button, turning off the power from the battery, they spring back apart because I have a little foam ball pushing them apart. So this is a relay. Now, some very clever engineers miniaturized the relay into something like this. I actually cut the top off this so you can see it, but there's a little coil in here that pulls this up and down, and this turns on and off 2 switches. So this is a double pole relay, so you can control 2 different circuits at the same time. If we put this little relay into our coherer, we will be able to detect a radio wave with a very small signal, and then by switching this little switch, we'll be able to control a bigger signal, maybe even big enough to ring a bell. Let's try it and see. I'm going to go ahead and unplug this because this is 110 volts. It's a little bit dangerous. Wouldn't want R51 coming in here with that now, would we? That would be bad. Okay, so here's the relay with the lid cut off. I've put another one here on this little circuit board that has the lid on it. And on this side, I have the power connected to the coil, to the magnet. So when you put power on these, it closes that coil. But you'll notice the power comes in here, and it has to go through the coherer to be able to get to that, and then it goes back to ground. So if this conducts, it will turn on the light, but the relay will also turn on the bell. Let's give it a go and see what happens. Now remember, the bell has a little switch, so when it gets pulled in, it disconnects, which makes it spring back out. So it gets pulled back in. When it springs out, it reconnects, the little switch reconnects, and so that's why it rings. So now, with just a little micro radio wave, we're able to detect the radio wave and turn on the light, but also to turn on this bell. Let's try it again. Okay, so here is the coherer. This is the cup, and the power is trying to go through here, but then it goes through the coil in the relay. And when the coherer detects a radio wave, it lets the power flow through, so the coil energizes and turns on the switch. The switch is like the 2 spoons touching together. They're hooked up to a battery, and then they make the bell ring. And there you have it. We now have something that could be used to send a signal by radio, because the radio wave has to be pretty strong. We don't know how to do our modern radio waves, so it's like a spark that transmits the wave, and that spark then makes these little particles. And remember, I made little aluminum balls so you can see them, but in the actual equipment that Marconi used, they just used little filings of metal in a tube, and when there was a radio wave, they conducted. When they conducted, it turned on the buzzer, and this little hammer on the buzzer, as it's going back and forth, they had it hit the coherer to turn it off. So the radio wave would turn it on, the hitting would turn it off, and if there was still a radio wave, it would turn back on, so it would just keep ringing until the radio wave stopped. When the radio wave stopped, that meant it was the end of it. If it stopped fast, it was a dot. If it lasted a long time, it was a dash. And so in this way, they were able to send radio waves through the air, Morse code. And it's fascinating to me to get this radio wave to go a long ways. Now remember, I'm in a room where there's a lot of radio waves from stations, but they're very, very, very weak. So it's not enough to make the coherer detect them. Back then, they didn't have radio stations around, and they needed a signal strong enough so a coherer could detect it a long ways away, And so they made great big sparks, some of them with 20,000 volts. And that's how they were getting a strong enough radio wave to go quite a distance. So I want to go back and make sure that we really understand the principle of using the relay. Remember the spoons. The signal to power this coil is a weak signal. But once it pulls the spoons together, they're big heavy spoons and they're touching, so we can put enough power through to run a motor or something big. If we ran that much power through the coil, it'd just burn it up. So a small signal can control a big one. And that's what we're doing over here, only we're doing it with a little tiny relay. And here we have a teeny coil. A very small amount of electricity is trying to go through this cup, and before it can get back to ground, it has to go through the coil. So if the cup is in the influence of the radio waves, then it will cohere these particles together and they will conduct a small trickle of power. In this case, just for you guys who want to know, I have about 40 milliamps going through here, and that's about the most they can do. This coil requires 20 milliamps. I'm also driving about 20 milliamps to the LED. It's just not enough without the relay. So with the relay, then I can control a big amount of power. The ability to use a very small signal, which is a signal you get by the radio wave making these little balls cohere, is magnified so you can control a great big power. That's exactly what we're going to learn next time about how we use vacuum tubes. A vacuum tube does this same function. When there is a signal present, it makes a lot of power flow, and this little micro signal, like a distant radio station, when it's off, then the power stops. And in radio waves, we turn it on and so fast, not for Morse code, we turn it on and off so fast that when we hook it up to a speaker, it sounds like someone's talking or it sounds like music. But it's just because it's turning on and off very quickly. We're going to learn how in a vacuum tube, you take the very weak signal of a radio wave and turn the vacuum tube on and off so it lets a lot of power through to be able to run something like a big speaker. See you next time. Woo! Did you get all that?
It's a lot to get, isn't there?
So I've got the coherer here, so this tiny little spark rings the bell.
That's pretty neat.
It really does work, and it's really amazing, isn't it?
Mm-hmm. So you have some advice from one of your students named Elijah.
Elijah?
Yes,
What does
He
Elijah
said,
say?
Leave the bell on in case R51 comes. Because you're in Area 51.
R51.
Yeah.
He better stay.
Leave the bell
We
on.
better make sure he's not in there.
It's a good idea.
Let's take a look.
Oh. Drinking your coffee?
So here I am in Area 51,
With your coffee.
just sitting here, having this nice beverage, enjoying my life. What's that? I don't. There's nothing in here. It's just for show. What is this? Oh my goodness. Can you believe it? Look what I invented. Look at this. I invented this. I think it's an airplane, and it's right.
Wow.
R51. Lady Page is going to be so happy to see you. Wait right here. Come on. Wait right here. I found her. Look, Lady Page, did you see what I invented? Look at her, she's so happy. Are you happy today? Okay. Let me explain to you how this works. This is a hair thing. This is a Go Hair thing. And what you do
is you wash your hair, and then you put these little balls, and it makes it look so pretty. And this thing here, this tells you when it's time to stop, okay? And see, you gotta have one of these. And with this, you can just go, can you hear that? Stop. It needs to stop. Don't worry, I can fix it. I stopped it. Oh, that's gotta make her think I'm special. But did you see this one over here? Look at this, Lady Paget. This is the biggest invention of the week. This is a high-powered superconductor collider. And watch this. Oh man, watch him go. Do you want to hear a song? Jingle bell, jingle. Listen, that's amazing. These things are just, whoa, can you believe it? And do you see these two spoons right here? What they do? Do you want me to show you what these two spoons do? Well, now watch this. They just go like,
You know, it kind of serves him right.
My hypothesis is R51's a conductor.
He is a conductor.
See you next time. Thank you.